A ball is launched horizontally from a height of 12.8 meters, and the table gives the x and y coordinates at half-second time intervals until it hits the ground. So we're going to do graphical analysis for the horizontal and vertical motion of the ball. So we know that in projectile motion, the horizontal motion has a constant velocity. So in part A, where it says use graphical analysis to quantitatively describe the horizontal motion of the ball, we know it's moving as a constant velocity in the horizontal direction, so we want to quantitatively describe it by giving a number value for that constant velocity. So since position versus time for constant velocity will already give you a linear function, there's no need to do any linearizing of the graph. We're just going to go ahead and plot x versus t. So you want to make sure that you label the axes. So the vertical axis, we're going to call it x, measured in meters, and the horizontal axis is time, measured in seconds. Make sure you put the labels with the units on there. And we can go from 0 to 4 seconds. Notice we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So roughly every let's just go every 2 lines and make that 1 second. So we'll have 0, 1, 2, 3, 4. Even though we could have filled up the entire graph by going every 3rd line, it just makes it easier because we have the half-second times in the middle, which correspond to that line directly in between them. And then on the vertical axis, we want to go up to, if we look at our maximum number, is 17.6, or since we have 4 lines on here, let's just go up by 5s up to 20. So we'll say this is 5, 10, 15, 20. All right, so let's go ahead and do a plot for x versus t. The first point is at 0, 0. Second point is at 0.5 and 2.2. So that's roughly there. Next point is 1.0 and 4.3. So somewhere around right there. Then we have 1.5 and 6.7. So that'll be somewhere around here. 2.0 and 8.9, about right there. 2.5 and 11.0, somewhere around there. 3.0, 13.1. 3.5, 15.5, and 4.0 and 17.6, and it does form roughly a straight line. So with a straight edge, you want to draw a perfectly straight line. Don't just connect the points if they don't form a perfectly straight line, but use a ruler and try and draw as best as you can through all those points. Now, since we know that v is equal to delta x over t, that was the equation we did back on day 1, if you rearrange this equation for delta x, to get delta x by itself, you get delta x is equal to v times t. The delta x is just the same as saying an x since it started from 0. So if we take the equation delta x equals vt and we compare that to the equation y equals mx plus b, well, the plus b is like a plus 0 in the equation since it passes through the origin. On the y-axis, we have the x, and on the x-axis, we have the t. So according to this equation, the slope of the graph is the velocity. So calculate the slope. Remember, for the slope, it's really important that you pick 2 points that are actually on the horizontal line that you drew, and not necessarily 2 of the data points. So since it passes through the origin, I'm going to pick 0, 0 as one of the points. And I'm just going to go ahead up here and say this is about, up here is about 4.5 and 20. So when I calculate the slope using y2 minus y1 over x2 minus x1, that should give you, let's see, so we have 20 on the y-axis, minus 0 divided by 4.5 minus 0, and that is equal to about 4.4 repeating meters per second. Okay, so the horizontal motion is not too complicated. The vertical motion, because we're doing position versus time, we know that the vertical motion in projectile motion is accelerated, so we have to come up with a quantitative value for the acceleration. If you try to plot the points in the table, the y versus the t, you're going to have points that kind of gradually form a downward curve. It's going to start kind of high up, and the points are going to follow this curve like that. So we need to find a way to linearize these points. So since the object was launched horizontally, that means the initial vertical velocity was 0. So with an initial vertical velocity of 0, we can look at the equation delta y is equal to VOT plus 1/2 AT squared. And the reason we picked this equation is because with that initial vertical velocity going to 0, this is the only equation that gives you a relationship between the y position and the time, which is what we want, since from the data table we have the y position and the time, given that it has a constant acceleration. So we cannot just plot y versus t. In order to linearize this, we have to plot y versus t squared, because when you take this equation and compare it with the y equals mx plus b equation, y equals mx plus b, since that term is gone, the plus b is like a plus 0 on the end. On the y-axis, we're going to just have y. On the x-axis, we're going to have that t squared. So what's left is the slope of this graph will be equal to 1/2 of the acceleration. So that's why we want to linearize this graph by squaring the time. So we're going to put on the graph, on the vertical axis, we're just going to have the y in meters. On the horizontal axis, we're going to have time squared measured in seconds squared. I'm going off the edge of the tablet screen now, so that's supposed to be a second squared right there. So I need to use the table to come up with a new row for time squared, measured in units of second squared. So I need to take all the values from the top row and just square them. 0 squared is 0, 0.5 squared is 0.25, 1 squared is 1, 1.5 squared is 2.25, 2 squared is 4, 2.5 squared is 6.25, 3 squared is 9, 3.5 squared is 12.25, 4 squared is 16. Sorry, it's not the best handwriting, but it's all I can do with this tablet. So let's plot the values of y in this row with the values of t squared in this row. So we're going to have 0 and, well, the first thing is let's go ahead and put the numbers on the axis. So on the horizontal axis, we need to go from 0 to 16. So I think we're just going to have to jump up by 2's. So it'll be like 0 to 4, 6, 8, 10, 12, 14, 16. And on the vertical axis for position, it goes up to 12.8. So we're going to round that up to, let's say, 16. So we'll make this 4, 8, 12, 16. And so first point is going to be at 0, 12.8. So around here. Next point is 0.25 and 12.6. So not too far away, really. Probably about like right here. Next point is 1 and 12.1. that's probably still pretty close there. All those are kind of jammed in pretty tight. Then 11, or 2.25, and 11. So that should be, I don't know, kind of around somewhere in that range. Then 4 and 9.5. So somewhere around there. 6.25 and 7.7. Around there. 9, 5.7. Should be right about in the middle of that block. 12.25 and 3.1. Around there. And then 16 and 0 right there. And now you can see that these points do form a straight line. So if we get the slope of this line, so the slope equals same formula as before, y2 minus y1 over x2 minus x1. We'll pick a point like somewhere up here and another point somewhere down here. And remember, it doesn't have to be the exact, it's best not to be the exact data point, it's just something that's on that line. So let's say roughly about, let's say this point is, I know the actual point on there is 0, 12.8, so let's just say 0, 13 is the point that's on the line. And let's say down here, let's just go ahead and say this one is 16, 0. So the y-coordinates is going to be 0 minus 13. The x-coordinates would be 16 minus 0. So we have negative 13 divided by 16, which gives a slope of negative 0.81, roughly. And remember, we said the slope is equal to 1/2 of the acceleration from this equation. So that means that the acceleration should be double the slope. So the acceleration here looks like it's going to be roughly negative 1.62 meters per second squared. The acceleration is negative because it's going, the acceleration points in the downward direction. So why didn't we get an acceleration of negative 9.8 or something close by? Well, notice this problem never said it took place on Earth, and I deliberately picked that because I didn't want people to just automatically assume that you're going to get an answer of negative 9.8 meters per second. In fact, from this acceleration, it's likely that this took place on the moon because, as you saw in some of the linearization problems we did in class, the acceleration of gravity on the moon is about negative 1.6 meters per second squared.